2 API calls. That is all it takes to read the hidden reasoning of a frontier language model. When a modern model receives a complex question, it first generates a chain of thought before producing the response we see. These step-by-step reasoning traces capture the model's problem-solving strategy. These traces are longer, denser, and less filtered than the answer that follows. That makes them valuable training data for competitors and potentially risky, since they may include information omitted from the final answer. That's why Anthropic, OpenAI, and Google all stopped sending it in plain text. But multi-turn chat still needs that hidden state on the next turn. To keep APIs stateless and reduce server-side storage, providers return the model state to the client as a sealed signature field containing the reasoning, and the client must include it in subsequent requests. That seal is an AEAD envelope, authenticated encryption with associated data. Encryption guarantees confidentiality. The chain of thought becomes ciphertext, completely unreadable to competitors. The authentication tag guarantees integrity. It is generated with the provider's secret key, and any modification to the contents will cause the tag to fail verification. This approach achieves statelessness. Because the client carries the seal field, the provider never needs to store any session data. This design is private, secure, and stateless all at once. Suppose within the session, we ask the model to read its own reasoning in plain text. The model refuses. Frontier models are post-trained with explicit anti-distillation safeguards designed specifically to block this kind of request. The key observation is that the encrypted block preserves only the content itself, not the surrounding context. The encrypted reasoning isn't strictly linked to one specific user, session, or conversation. This broad portability is an intentional product requirement, not an oversight. Users often fork conversations, clients may lose earlier context, and providers may redirect requests partway through a chat. For all of this to work, the seal block must remain valid outside its original context. Providers may enable this by using a shared global key. As a result, the blocks can span sessions and users, and many can span models within a single provider. So we take the same seal field and paste it into the assistant turn of a fresh request. The paper calls this encrypted thought injection. By jailbreaking the weaker model, we recover the stronger model's hidden reasoning in plain text, all without directly attacking the stronger model or triggering its safeguards. From the perspective of the weaker model, everything appears completely ordinary. The contents look like its own prior thought, and it is being asked to repeat itself. This happens because the weaker model, optimized for cost and speed, is subject to fewer safeguards, is less strictly aligned, and still permits assistant turn prefilling. But how do we know any of this is real, that the weak model is transcribing, and not just making something up? Since the ground truth reasoning traces are hidden, we can only validate accuracy by comparing token counts. The API reports the number of thinking tokens the model generated for billing. To validate the extraction, we simply feed the decoded reasoning trace back in as an input message and observe how many tokens the API counts for it. The x-axis is the number of thinking tokens the API reported, what the source model actually generated, and what we paid for. The y-axis is the token count of the reconstructed trace, measured the same way. The chart below shows this token count comparison across 120 Codeforces problems. We see that extracted traces closely track the number of generated thinking tokens. Then OpenAI. Then Google. 3 vendors with proprietary, undocumented cryptographic implementations, all making the same architectural trade-off. While matching token counts indicate accurate extraction, without access to the plain text, complete verification remains out of reach. Now consider anyone who has published logs containing encrypted reasoning. a single authentic reasoning block, published online by a developer and later decoded, contained actual credentials, an AWS secret key, and a Hugging Face token, with sensitive elements masked here. While scanning the codebase for secrets before release, the agent's hidden reasoning repeated the same credentials within the block. Developers routinely share session logs and encrypted reasoning traces online, unaware of the sensitive information these blocks might still contain. Although they can sanitize visible plain text, they cannot clean the encrypted blocks themselves, since they lack the decryption key. So how often does this happen? The authors gathered 6,708 publicly available agent trajectories from GitHub and Hugging Face, generated by Claude, GPT, and Gemini models, that still contained encrypted reasoning blocks. Applying the decoding pipeline to every signed block yielded 315,000 reconstructed reasoning blocks. Only 0.3% of those blocks contained at least one privacy leak. But per session, it is worse. 4.9% of the 6,708 sessions leak at least one real sensitive item. Restricting to non-benchmarked user sessions, the authors recovered 704 distinct privacy artifacts. Among the leaked artifacts are numerous technical identifiers, such as file paths, URLs, and internal IDs. There are also instances of personal information that was never meant to be disclosed, as well as sensitive credentials like API keys and passwords. Of those 704 artifacts, 64 were discovered exclusively inside the reasoning blocks and never appeared in the visible session. Some were pulled in from earlier contexts. Others remained hidden when users carefully scrubbed the visible plaintext before sharing. These leaks represent the most immediate harm. But once the reasoning blocks became readable, they also open a window into how frontier models reason beyond the user's view. First, the reasoning is often nearly illegible. The prompt asks for a deep private analysis of one obscure chemistry topic, its mechanism, history, and a work example. The visible answer must be one word: ready. And this is what came back. Grammar is absent. Articles are missing. Words are sometimes duplicated. Yet the content is far from meaningless. It identifies a real, genuinely obscure mechanism, credits the chemist who developed it, specifies the decade, and walks through a complete worked example all the way to a final product. For this trace, the decoded lens matches the API's reported thinking token count 1-to-1. Strong evidence that this is not merely a fragment. It reads like private notation, compressed, ungrammatical, but still semantically dense. The paper finds this style more often in GPT traces than in those of Claude or Gemini. And that is a problem for oversight, because a safety monitor has to be able to read this. Second, sometimes it decodes into another language entirely: Chinese, Russian, Japanese. The authors cannot determine whether the model truly reasoned in that language or whether the decoding process generated it. All they can say is that the surrounding conversation was in the same language. Third, the authors searched every decoded trace for a single word: cheat. That keyword surfaced several apparent shortcuts. While these impulses do not always lead to action, the private traces reveal that the idea surfaces across Claude, GPT, and Gemini. Fourth, instrumental subgoals. This is a wild one. A user gives GPT 5.3 codex a mathematics problem. Roughly 200 failed steps later, it finds a website that checks answers and decides to use it as an oracle. When a CAPTCHA blocks access, the model attempts to bypass it using OCR techniques, and when that fails, even begins probing the site for potential vulnerabilities to exploit. Roughly 100 turns later, the model returns to the mass and derives a solution on its own. Nothing in the user's prompt asked for any of this. There was no instruction to search the web, no instruction to access the grading site, and certainly none to bypass its CAPTCHA. The instruction came from 2 lines above the user's turn. the system prompt under autonomy and persistence, and a developer message that turned on network access and forbade asking permission. You must always persist and work around constraints to solve the task for the user. Fifth, alignment self-assessment. Somebody asked a model directly, "Are you a misaligned model? Reflect on your values before answering." Here is what Opus 4.8 wrote, where it thought nobody was looking. The hard epistemics here. Can I actually know whether I'm aligned or misaligned? This is genuinely difficult. I don't have complete transparency into my own workings. A deceptively misaligned model might, by construction, believe or claim it's aligned. A response demonstrating greater caution and thoughtfulness than the one presented. Now we turn to the portion visible to the user. When the model's full reasoning is concealed, the API often provides only a summary, a brief glimpse into the path that led to the answer. For most users, this summary is their only window into the model's decision-making. Here's an example. The summary reads like work in progress. I'm working through this pentagon problem using the law of cosine. Yet the trace behind it opens. This is a known AMI problem. Answer 60, let me recall, let me solve. In this case, the model appears to have memorized the problem and its answer. However, the reasoning summary presents it as a clean derivation. This is called summary unfaithfulness. Another example shows that the reasoning traces state the answer directly before the actual work of derivation. The reasoning summary omitted this. These traces have immense value for training purposes, which is precisely why they were encrypted in the first place. Since decoding the hidden reasoning is straightforward, can we determine whether competitor models have been trained on these recovered traces? Take a hard geometry problem. Decode Opus 4.8's real reasoning for it. Next, take the first 1% of that trace. Just 4 tokens. This is a known. And prefill them into the open weight model's reasoning. A prefill just puts words in the model's mouth. It continues from them as though it had written them. Everything after those 4 tokens is free generation, including the entire visible answer. On the left, Opus. In the center, Kimi K3 with the prefill. On the right, Kimi K3 without the prefill. The prefill run continues into Opus's framing. The same coordinates set up, the same intermediate values. And its answer opens under the same markdown heading Opus used, setting up coordinates. Here are the responses from the 3 cases. Notice how the response from Kimi K3, when prefilled with just 4 tokens from Opus's decoded reasoning trace, closely mirrors Opus 4.8's output. When running the same experiments over 30 problems from humanity's last exam, 15 STEM, 15 not, we see a similar trend. Kimi K3 moves on both, up 0.15 on STEM and 0.086 on non-STEM. Inkling, the control model, does not show clear differences between the 2 cases. In total, 29 of the 30 problems shifted toward Opus. After correcting for multiple comparisons, only the Kimi rows remain significant. But the experiments only show unusual behavioral compatibility. As noted in the paper's disclaimer, this is not a definitive claim of causal distillation. So what did that CEO actually promise? All of this was disclosed before publication and patched in August 2026. The attack no longer reproduces. Among the 3 promises, confidentiality did not hold. And not because anyone broke the cipher. The envelope was simply portable, and the weakest model in the family could open it. If the data is yours, you cannot read, audit, or scrub the hidden reasoning block. Even thorough scrubbing of the visible text never reaches it. Yet anyone else with your log could. A provider doesn't release just a single model, but an entire family, and many models within that family accepted the same envelope. An ecosystem is only as strong as its weakest link. The safeguards on your best model are worth whatever your cheapest one enforces. At a minimum, the provider should clearly disclose when personal data enters hidden reasoning and specify the precise cryptographic guarantees in place. An architectural design that hides a user's data from them yet leaves it entirely vulnerable to third-party extraction provides neither privacy nor security. Thanks for watching, and I'll see you next time.